Okay, so example 2 is a more representative example of the sorts of things we're going to do in optimization. And so this is one where a picture is definitely going to help, and we have to be kind of careful about the constraint and the function that we're trying to maximize. All right, so we start off this one where we have 20 square feet of cardboard, and from that cardboard we're supposed to make a rectangular box where the base of the box is a square and the box doesn't have a top. So it's going to have a bottom and 4 sides, a square base, and no top. So we need to think about getting a picture for this situation. All right, so I'm going to sketch a picture up on the board and see how this goes. So I want a square base. Here are my sides. Now, because the box doesn't have a top, I can actually see these bottom lines. So this is my open top rectangular box with a square base. Now, since the base is square, I know that the dimensions of the bottom are the same. I don't know what they are yet. We're trying to find that. But I'm going to call those x because they are the same. And then the height will be y. Right? So we have 2 variables. We don't know either one of them. X is the dimension for the base, and y is the height of the box. Okay, so in this one, I think it's easier to start with the target. We're trying to maximize the volume of the box we can make with the supply of cardboard that we have. So the volume of a rectangular box is length times width times height. So that's x times y, or x squared y. Right? That's our volume. And now we need to eliminate one of those variables so that we can actually take derivatives and solve the problem. That's where the constraint comes in, that we're not just building a box using as much material as we want, right? We only have 20 square feet of cardboard. So we have to understand that that 20 square feet of cardboard represents the area of the base and the sides that we can use. So we're going to look at the area, or the amount of material that the box requires. We have the base of the box, which would be an area of x squared, x times x. And then each of the sides, right, has a base of x and a height of y. So I have x times y is the area, or the amount of cardboard for each one of the sides, and all the sides are the same, and I have 4 of them. So the area, or if you like, the amount of material, is x squared plus 4xy, and that is constrained by the amount of material that we have. It's 20 square feet. So I want to use this constraint to get y in terms of x. So I'm going to move the x squared over, and then I'll divide both sides by 4x. We could rewrite this, but maybe it's just as easy to leave it for now, and then we'll do a little bit of algebra after we make a substitution. All right, so I'm going to take my volume equation, and in place of the y, right, I'm going to use this value. And then this is nice. The x squared in front will cancel, or one of the x's on top will cancel with this x in the denominator. So instead of x squared over 4x, I'm going to have x over 4 times 20 minus x squared. And finally, if I multiply through, I'll get 5x minus x cubed over 4. Okay? So that's my target function that I want to find the maximum for, but it's now only in terms of one variable. So this is something we can work with. Our process is to take the derivative. In this case, I'll get 5 minus 3x squared over 4. Right, this is like the example we did last time where the 4 in the denominator doesn't mean do a quotient rule. It means think of having 1/4 as a constant out in front. And so the derivative is 1/4 times the derivative of x cubed. That's 1/4 times 3x squared, or 3/4 x squared. That exists everywhere, so I just need to set it equal to 0 and solve. If I clear the fractions, I'll get 20/3 is equal to x squared. And so x is the square root of 20 divided by 3. We're dealing with an actual box, and so we can ignore any, right, if x squared was 20 over 3, we could have minus the square root of 20 over 3, but that doesn't make sense when you're building a box. So we can ignore that negative answer. And I'm just going to get a decimal approximation here. Take a square root. So x is about 2.58. Right. That's our only critical value to deal with. And we'll test it using the second derivative. Right. So if I come up here, v double prime would just be, let's see, minus 6x over 4, sorry, yeah, minus 6x over 4, which is minus 3/2 x. If I plug 2.58 into that, then I get something negative, right? I have minus 3/2 times 2.58. So at 2.58, minus 3/2 times 2.58, which is negative, don't care about the value. And so x equals 2.58 is the max. Like in example 1, it's the only critical point, and it's a max, and the second derivative for any positive value of x is going to be negative. So the function's concave down everywhere, which means this relative max is also our absolute max, right? It's the only one, and the function is concave down everywhere. So the last thing to do is to get the dimensions of the box. So I need both the x and the y, and I need to give some context or units. Right? So if x is 2.58 feet, y will be, let's see, where's my constraint? It's right here. 20 minus 2.58 squared over 4 times 2.58. And that ends up being about 1.29 feet. So these are the dimensions of the box. And what that means is that the base, right, is basically a 2.5 foot square, and then the height of the box is about 1/2 of what the base would be. All right. So if you had 2.5 foot by 1 1/4 foot tall. We're not asked to find the maximum volume, but we could just by taking 2.58 squared and multiplying by 1.29. That would tell us the actual volume that we could enclose when we only have 20 square feet of cardboard. That's example 2. We'll do example 3 in just a minute.